Last time we talked about analyzing DC circuits using a series parallel method whereby we could reduce the circuit to one battery or power supply and one equivalent resistor. Sometimes you run into a situation where that isn't possible, and yet you want to find things like currents or voltages in a given circuit. There's a beautiful procedure that we can use to solve a much more complicated circuit. It's called Kirchhoff's rules. It's the Kirchhoff rule method. And so we'll begin with, I'll just state the two Kirchhoff rules, and we'll go on and do an example. First of all, the junction rule. The junction rule says that the sum of all currents entering a junction is equal to the sum of all currents leaving a junction. This rule is based upon fundamental rule of the conservation of charge, a fundamental notion in physics. The Kirchhoff loop rule says that the algebraic sum of changes in potential across all elements in the circuit around a closed loop is 0. That's based upon the conservation of energy. So even though these are sort of operational tools to solve a circuit, the consequences are fairly far-reaching, two fundamental conservation laws in physics. There are some other operational procedures that you want to be familiar with. If you're going around a circuit and you traverse a resistor in the same direction that you've chosen the current, we add a term to the equation minus IR. If you traverse a resistor in the opposite direction that the current is assigned, you add a term plus IR. Furthermore, for number 3, if a battery is traversed from the minus to the plus end, we add a term plus E for electromotive force to the equation. If a battery is traversed from the plus to the minus, the long end to the short end, we add a term minus E. Now, how does all of this work? That sounds like a lot of gobbledygook. Let's apply it to a real circuit. Typically what happens is in a Kirchhoff rule problem, we might get a circuit that looks something like this. So it's complicated. I've got 3 batteries in the circuit. I got a bunch of resistors. And typically the question is to find all branch currents. Now, you'll notice in a circuit such as this, we have 2 loops, and we have, as it turns out, 3 currents. So I have a branch of current that could start at this junction. Let's start at this junction. And I1, I've chosen to go from this junction down here through these elements up to this junction. That's what I call I1. I2 is the current that's going from down here through these elements and into this junction as well. And I3 is the current that I've chosen to go between these 2 points, these 2 junctions in the circuit. That covers all the currents in the circuit. If I can calculate I1, I2, and I3, I now have calculated all of the branch currents in the circuit. And that's typically the gist of a Kirchhoff's rule problem. There are some variations on the theme, but this is the basic way. Now, so how do we do this? First step, when you see the circuit, is to draw the currents going into and out of the junction. You don't have to know which way they go. You can guess. And so I just made a guess. It's based on nothing. If it turns out that your guess is wrong, there's no penalty. It just means you'll get a negative current, which means that at the end of the problem you say, oh well, I picked wrong for the direction of the current to begin with, but it's not a big deal. So what I did was I chose three directions. I chose I1 to be going into this junction, I2 to be going into this junction, so I1 comes this way, I2 comes this way, and I3 is going from this part to this junction to this junction. That covers everything. According to the rules, the junction rule, the sum of the currents going into the junction equal the sum of the currents going out. Therefore, I1 plus I2 is equal to I3. Next, we draw two loops. And again, it doesn't matter if you make them clockwise or counterclockwise, because the sum of the voltages around the circuit will be zero. So whether you go clockwise or counterclockwise doesn't matter, as long as you correctly apply the calculational tools. So let's go to this left-hand loop. As you see, I drew it, this left-hand loop, as you see, I drew it in a clockwise fashion. Let's start at the 6 volt battery. So when I go, let's say I'm starting here, I'm going little to big or negative to positive. That means I add a term plus 6 volts. I'm traversing a 3 ohm resistor, therefore I'm adding a term and I'm traversing this resistor in the same direction I have designated current I1, therefore I add a term that's minus 3 I1. Now, to continue on the loop, I'm going down, I'm traversing this 4 ohm resistor through the loop in the same direction I designated I3, therefore I put in a term minus 4 I3. I'm traversing this battery, again, little to big or negative to positive, so that's going to mean plus 12 volts. I'm traversing this resistor. Would help if I put the size of the resistor on there. The size of this resistor is 2 ohms. So this gives me a term, I'm going in the same direction as the current, so that's going to be a minus 2 times I3. I am now going around the loop continuing. This is a 2 ohm resistor going in the same direction that I1 is going. Remember, once I pass this junction, I'm back to I1, so it's going to be minus 2 I1. Then I'm going to traverse this 7 ohm resistor, again in the same direction as the current is going, so it's going to be a minus 7 I1 equals 0. Let's go to the other side of the circuit. Let's start at the 9 volt battery. I'm going from minus to plus, so that's a plus 9 volts. This is going to be, I'm traversing the 5 ohm resistor and the 12 ohm resistor in the same direction that I2 is designated, so it's going to be minus 5 I2 minus 12 I2. I'm traversing the 4 ohm resistor in the same direction I3 is going, so that's going to be a minus 4 I3. I'm traversing the 12 volt battery from little to big, so that gives me a plus 12 volts. I'm traversing the 2 ohm resistor in the same direction I3 is going, therefore it's a minus 2 I3. Then I'm traversing the 6 ohm resistor in the same direction that I2 is going, as well as the 4 ohm resistor, so it's a minus 6 I2, a minus 4 I2. I'm traversing the 9 volt battery. Oh, I'm back to the 9 volt battery, so I'm there, I'm done. This all equals 0. Notice I have 3 equations and I have 3 unknowns. At this point, and we can put all the terms together, we want to make it a little bit cleaner, so I1 plus I2 equals I3. I've got 3I1 minus 2I, minus 3 minus 2 minus 7. That's a minus 12. I1, 6 and 12 is 18, plus 18 is equal to 0. Then I have 9 plus 12 is 21. Then I have minus 5I2 minus 12 is minus 17. Minus 10 is minus 27. I2 and minus 4, minus 2, so it's a minus 6i3 equals 0. So now I have three equations, a little cleaner, three equations and three unknowns, and you have three ways that I know of that you can solve them. The most direct way, the way that most people use, is to solve three simultaneous equations. Oftentimes the best way to start in this case is to start with this equation and substitute perhaps in the, let's see, so I have, I'm missing a term here. This should be minus 12i1 and it should be minus 6i3 here equals 0. There, that's better. Okay, so the best way to do it is to perhaps solve for one of the other variables in here. So maybe I would replace I1 by I3 minus I1, I'm sorry, I3 minus I2 equals I1. So then I would have two equations that just have I3 and I2 in it, solve two equations and two unknowns, and so on. That's one method to use. That's usually the most direct method that people use. Another way to do it is to set up a matrix, a 3 by 3 matrix with 4 solutions on the right. Row reduce the matrix until you start with your 9 matrix elements and your 3 values on the right. Row reduce the matrix until you have the identity matrix. And the 3 values that you have essentially will be the 3 currents, not necessarily in this order, but you'll get the 3 currents. That's a way that people tend not to use, although it's a nice way to solve it. It's a nice way to use your linear algebra skills. The third way to do it is, of course, nowadays people have programmable calculators where you can plug in 3 equations and immediately come up with your 3 eigenvalues just by punching the equations into the calculator. That's perfectly valid. I certainly allow my own students, if their calculator will perform those functions for them on an exam or what have you, they can use it and not have to take chances on making algebraic mistakes, which people tend to do. I don't know how other faculty members try to grade such problems, but I tend to give most credit for just getting the loop and junction equations consistent, and then not so much in case if an algebraic mistake is made. But the thing we're most interested in is that you set the 3 equations up properly using Kirchhoff's rules. We won't go through the algebra here, but I will state if you want to work this through yourself, I'll state the answers. By the way, this was a problem that appeared on the circuits test last semester. It turns out that this is 0.84 amps. I1, I2 was 0.48 amps, and I3 was 1.32 amps. So this is a really nice way to solve much more complicated circuits than the ones that you can solve simply with a series parallel representation where you get an equivalent resistance. Nice method, takes a little bit of practice, but once you've done about 3 to 4 of them, I think you'll feel at home with the methodology, and you'll be quite successful in solving these problems. Next time, we'll talk about RC circuits, so we'll add capacitors to the mix along with resistors.